this is 2019 problem 2, number 3. Looks like this. Okay. All right. So 2019 set 2, number 3. All right. So we've got this picture. I'm going to kind of redraw what's going on here. We're going to release this little rock or sphere of mass m and radius little r up here at the top. It's going to fall some distance h. It's going to go through this loop that has a radius big R, and there's a point A up here that we're going to talk about. And they tell me that in this they say that R, when you see that, that tells you that this big R of this circle is much, much bigger than the little r that you have of the sphere. So it says not drawn to scale, so there's a very large difference. So that's nice. That helps us not have to worry about that in this first part. So I is equal to BMR squared for this little sphere. All right, so they say they use this track and they send it around the track, and so on A, it says determine or derive an expression for the minimum speed of the sphere's center of mass that will allow it to just pass this point without losing contact with the track, and express your answer in terms of B, M, R, and fundamental constants as appropriate. So when I get to point A, okay, I'm in a loop. Anytime I go in a loop, I think, oh, centripetal force. So if I just get to the top, so this is at point A, the first force I think of that I have is gravity. Now, if I'm just barely going fast enough, because remember I'm upside down, so if I'm just barely going fast enough, I have to have a centripetal force to the center to keep me on this track. If I'm just going fast enough, these two are equal. If I'm not going fast enough, this is not big enough and I fall. If I'm going faster than I have to, then this is not enough and I get a normal force. This is like when you spin like something in a bucket or a cup. If you put liquid in it, you spin it above your head, you can spin it completely above your head and it won't fall out if you spin it fast enough. So to just make it, that centripetal force is equal to gravity. And centripetal force is mv squared over r, which in this case is big R. You gotta be careful with the writing here because I wrote little r at first too. But it is that r that's in this equation is the radius of the loop that it's on. So that's the big R, not little r, because little r is the radius of the sphere. That's gonna equal mg. So this goes away, this goes away. I'm gonna multiply both sides by r. I get v squared is equal to gr. And then I take the square root of that. So v is gonna equal the square root of gr. And that's how fast I have to be going at the top. So that's a really simple calculation. Just remembering that you have to have a centripetal force to do that. Now they say, okay, suppose that you do this and you release it with at rest and it rolls without slipping. Derive an equation for the minimum release height. So how high do I have to release it up here? How high does it have to be released from here such that I get here and have that velocity that I had, because it says minimum, so I got to get the minimum. So I know that I'm going from up high down here, so this is all potential, all kinetic, and a mixture of the two. And so what I'm looking for is what's happening here versus here. So I'm going to write a U naught plus a K naught equals a U final plus a K final. So U naught is what I'm looking for. That's mgh. K naught is 0 because I'm released from rest. U final is not 0. It's mgh, and my h would be this, which would be r plus r. So that is 2r. My kinetic energy final is going to be 1/2 mv squared, but don't forget it's rolling, so you also have 1/2 I omega squared. Okay, and this is vcom right here. That's what that is. I didn't write vcom on the bottom of that. All right, so let's do a little figuring here. So we've got MGH is equal to 2 MGR plus 1/2 MV squared plus 1/2. Now I, they told me, was BMR squared. And then omega, we all know that V is equal to R omega. So omega is going to be V over R. So I'm going to plug that in here. Okay, now what this is going to do is it's going to help bring things together. So I'm going to go ahead and write MGH over here is equal to 2 MGR plus 1/2 MV squared plus 1/2 BM. Now, I've got R squared here. This R is going to get squared here, so these two are going to cancel each other out. That V is still squared, so I get V squared. Now I'm going to cancel out things I see that are the same. I see mass everywhere, so I'm going to go ahead and get rid of that. So I've got GH is equal to 2R plus 1/2. Now, V is not allowed. That was not on my list of possible things. So I go back to the velocity that I had, which is square root of GR. If I square that, then this just comes out of the radical. So instead of V squared, I'm going to write GR plus 1/2 B GR, because V squared would be GR. Okay. Again, if you're confused about that, V is square root of GR, so I square it so it comes out of the radical, and there it is. So then I get GH is equal to, now we're going to combine all this stuff. So these are all over 2, so I'm going to put this over 2, so this is going to be 4/2 R, 4R over 2, plus GR, oh, there's a G in there, I lost a G. It's 2GR. Okay, so GR over 2 plus BGR over 2. All right, then I can combine these. First of all, I see a G here, 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 and here. So I'm going to kill that. So here's my H. I'm going to get it. So 4 plus 1 is 5. So I get 5R over 2 plus BR over 2. And I would probably just leave my answer like that. Because you could factor out that R and say, okay, it's going to be, R over 2 times 5 plus B. But I just leave it like that. Okay, moving on. All right, now tell me that they take some data. The students perform this experiment, and here's some data, and here's some B values, and here's some H values. All right, and it says on the grid below, plot the height as a function of B, clearly scale and label all axes, including as appropriate, draw a straight line that best fits the data. Okay, now this, I do not have graph paper with me at present, so I'm going to freehand this. They tell me to do H as a function of B. Remember, that's always Y as a function of X. So this is what I've got going on. And they give me 4 big grids, so I'm going to go ahead and do 1, 2, 3, 4. And they give me 4 big grids this way. So 1, 2, 3, 4. I'm trying to equitably distribute these. Again, if you have graph paper, that makes it a little nicer. I just don't have any handy right this minute. All right, so I'm going to take these values here, and I'm going to plot them on here. So I'm looking at what do I got to scale my axes at. So my B goes from 0.4 to 1. So I got to get to 1. So that's a pretty easy division. So 1 divided by 4 is 0.25. So I'm just going to do this. Okay, there's a 1 there. Kind of met my line. Okay, then on the other way, my H's go from 1 to 1.2. So I don't want to start at 0. So I'm going to start, you know how you get those little division things and you say, okay, well, this is going to be 1 down here. So this is going to be 1.05, 1.1, 1.15, and 1.2. So I'm going to divide that out. That way my graph fills the whole space, or at least most of the space. All right, now I'm going to start plotting. So B is 0.4, and again, I have to do a little bit of estimating here, but that's okay. 0.4 and 1.08, so somewhere about here. 0.67 and 1.13. 0.5 and 1.1 and 1 and 1.2. Okay, now if I have a ruler, which again, I'm totally prepared for this, I do not have one. I'm going to draw a best fit line through that data. Okay. So that's what it tells me to do. Okay, now on D, it says they said the students repeat this experiment with the partially hollowed sphere and determine a minimum release height to be 1.16 meters. And they say, what is B for that? So they want a relationship between these two. Well, I did a graph. And anytime you do a graph, you probably need to do one of two things. You probably either need to get the slope of the graph or you need to get the area under the graph. This is a nice straight graph, so this is going to be a slope thing. So my slope is going to be my rise over my run, which is going to be my change in H over my change in B. So I can get a relationship between H and B here, and I've got a line. So if you have this on a grid, you could just go to 1.16 and then, go over and extrapolate down. So that is a possibility if you have a beautiful grid. I don't have a beautiful grid, so that's a little difficult, because if I went over here and then came down here, it looks like it's between 0.75 and 1. I don't know exactly. So I'm going to find the slope of my line. Now, again, this is a kind of a no-no. I would normally use places where the grid markers cross, but these lines, these look like they all fit, so I'm going to go ahead and go with data points this time, which is, again, probably a no-no, but I'm going to do it this time just for illustrative purposes. And this one is 0.4 and 1.08. I'm going to use those 2 points. So I'm going to use 1.13 minus 1.08, and I'm going to put that over 0.67 minus 0.4. So get 0.05 divided by 0.27. So I get a slope of 0.185. I'm going to keep all of that for just a minute. Okay, so that's my slope. So now if I have a relationship between these two, I'm going to put them into a point slope formula. And B is my X, and then this is my Y. And I'm going to use a point from the graph. How about we just use this one, 1 and 1.2. Okay? So I'll use that. So this is going to be my X that I'm looking for. So I'm going to put that in here. And I'm going to put the Y that goes with it right here, 1.16. And then I'm going to use this one. So minus 1.2. My slope is 0.185. And I'm going to subtract 1 over here. So I'm going to do 1.16 minus 1.2, so that's going to be negative 0.04 is equal to 0.185 times B minus 1. I'm going to divide by 0.185. So 0.4 divided by 0.185 gives me 0.216. That's negative, is equal to B minus 1. I'm going to add 1 to both sides, and so I'm going to find B is, it's about 0.8. So, I could round that, 0.784, so we'll say 0.78. So there's the B value for that sphere. Now, if you look at the answer guide, I believe they have 0.8. So, I'm really close to do with a freehand graph that it's, it's not bad. All right. Now, on E, it says calculate the radius of the loop. So I go back to what I had. Okay, I'm going to use this equation that I had for potential energy. So I had height is equal to 5r over 2 plus br over 2. I'm going to plug in the height that they tell me, which is 1.16. I'm going to put R in, because that's what I'm looking for, and B is 0.78. So I get 1.16 is equal to 5.78 R over 2. I'm going to multiply both sides by 2. I'm going to get 2.32 is equal to 5.78 R. I'm going to divide by 5.78. And so this is going to give me my R, 2.32 divided by 5.78. So I find that my R is 0.4 meters. And that is my R. This would be another one of those things where if you messed up on part B and you didn't have this right, if you used what you had, you probably would get points. I'm not looking at the scoring guidelines right now, but that's usually how that works. The last question they asked me is they say, okay, so now let's say that this is we assume that this is much smaller, but let's say that it's not. What would happen then? So if it's not much smaller, when I go upside down, here's my picture. All right, when I go upside down, if my R is not much smaller, let's say my sphere is like this big, okay, then my center of mass is here. Well, my center of mass is not approximately R away, right? So therefore, I have a smaller R. If I have a smaller R, this R right here, that's going to lead to a smaller V. If I have a smaller V, that's going to reduce this side down over here. So if that reduces that down, then my H is also going to get reduced down. So it's going to be less than because of that.